Before we begin, think about this for a moment. Every time you flip a light switch, charge your phone, or turn on a fan, something invisible instantly travels through wires, crosses entire cities, and performs work for you. In this video, you're going to discover what electricity truly is, where it actually comes from, and why the simple act of turning on a light reveals something deeply surprising about how the universe really works. Before we dive in, make sure to subscribe to the channel and click the bell icon so you don't miss future videos where we explore science, technology, and the hidden truths behind everyday things. So let's take a closer look and talk about the mystery of electricity. Most people think they understand what electricity is. After all, we interact with it constantly. Right now, electrons are flowing through the device you're using. Electricity is powering the lights around you, keeping food cold in refrigerators, charging batteries, and running machines all over the world. It has become such a normal part of daily life that we rarely stop to question it. But here's a simple challenge. Try explaining electricity. What actually happens when you plug something into an outlet? Where does the power really come from? What is electricity at its most basic level? Many people answer with something vague. They say electricity is energy, or they say it is electrons moving through wires. Others describe it as current flowing from one place to another. But those answers don't really explain anything. They simply rename the mystery. Yes, electrons move, but why do they move? What is pushing them? And how does that motion suddenly become light in a bulb, heat in a heater, or movement in a motor? The deeper you look, the stranger electricity becomes. In fact, the truth is far more unusual than most people realize. The thing we call electricity is not just a convenient utility that powers devices. It is a visible example of one of the most fundamental forces in the entire universe. And the way we usually teach electricity hides how extraordinary it really is. We make it sound predictable and ordinary. But once you truly understand what is happening, you begin to see that we are interacting with something incredibly powerful and deeply mysterious. Let me show you what I mean with a simple experiment. Take a piece of plastic wrap and tear off a strip. Now rub it quickly between your hands, as if you are trying to warm them up. After a few seconds, bring the plastic close to the back of your hand without touching your skin. You may notice something interesting. The tiny hairs on your arm begin to move. Some of them stand up and lean toward the plastic. The plastic is pulling on them. Stop for a moment and think about that. All you did was rub a piece of plastic. There were no batteries, no wires, no electrical outlet, and no visible power source. Just friction between your hands and the plastic. Yet now that piece of plastic can reach across empty air and tug on the hairs of your arm. How is that possible? In everyday life, forces seem to require contact. If you push a chair, you must touch it. If you lift a book, your hand must hold it. Everything appears to work through physical contact. But in this experiment, the plastic is not touching your arm. There is empty space between them, and still, a force is acting. Most people quickly dismiss this phenomenon. They call it static electricity and remember it as a small classroom demonstration from school. But what you just witnessed is far from trivial. You are observing the same fundamental force that holds atoms together, the force that allows chemistry to exist, the force responsible for your muscles contracting, your nerves sending signals, and your eyes detecting light. It is one of the four fundamental forces of nature. And in that simple moment with a piece of plastic, you saw that force acting across empty space. The reason we overlook how incredible this is comes from familiarity. Electricity is so common that we no longer notice how strange it truly is. We treat it like an ordinary tool instead of recognizing it as a window into the deepest structure of reality. To understand electricity properly, we have to slow down and examine what really happened during that simple experiment. When you rubbed the plastic, something important occurred on an incredibly tiny scale. You transferred electrons. Some of the electrons from your hands were scraped away and collected onto the surface of the plastic. It might sound insignificant, but even a small piece of plastic can gather trillions of extra electrons during that process. And once those electrons build up, something remarkable begins to happen, because electrons strongly repel each other. This repulsion is not a weak effect. It is one of the most powerful forces in the universe. When extra electrons accumulate in one place, they push against other electrons nearby with tremendous strength. And even the tiniest imbalance can create forces large enough for you to feel with your own skin. That small experiment with plastic and your arm hairs is actually your first glimpse into the enormous power hidden inside the electromagnetic force. When the plastic collects extra electrons, those electrons do not peacefully sit next to each other. They repel each other with an intensity that is almost impossible to imagine. Electrons strongly dislike being close to other electrons because they all carry the same negative charge. To understand just how powerful this repulsion is, consider a simple comparison. Take two electrons and place them about 1 centimeter apart. Even at that distance, the electromagnetic force pushing them away from each other is unbelievably strong. In fact, it is roughly 10 to the 42nd power times stronger than the gravitational attraction between them. That number is almost beyond comprehension. 10 to the 42nd means a 1 followed by 42 zeros. Compared to that level of strength, gravity becomes almost meaningless for particles like electrons. For electrons, gravity is essentially irrelevant. The electromagnetic force dominates everything. And this raises an important question. If the electromagnetic force is so incredibly strong, why does matter remain stable? Why doesn't everything explode apart because of these powerful repulsive forces? The answer lies in something surprisingly elegant: balance. Inside every atom, there are both positive and negative charges. At the center of the atom sits the nucleus, which contains positively charged particles called protons. Surrounding that nucleus are negatively charged electrons. Positive and negative charges follow a simple rule: opposites attract and like charges repel. The attraction between positive protons and negative electrons is just as strong as the repulsion between electrons themselves. These forces balance each other with incredible precision. Because of this balance, atoms remain stable structures. Protons pull electrons toward them, while electrons repel one another, creating a stable arrangement that forms the basic structure of matter. In everyday materials, there are enormous numbers of positive and negative charges packed together. Protons and electrons sit extremely close to each other, and their opposing forces cancel out almost perfectly. This cancellation makes most objects electrically neutral. But something important is still happening behind the scenes. Even though the charges balance, the underlying electromagnetic forces are still there. They have not disappeared. They are simply balanced so precisely that their effects cancel each other out. This means that the stability of ordinary matter depends on an almost perfect equilibrium between powerful forces. And when that balance is disturbed, even slightly, the effects become noticeable. When you rubbed the plastic earlier, you did not move a huge number of electrons compared to the total number inside the material. In fact, you may have moved only 1 electron out of every trillion. That might sound insignificant, but consider the scale of these forces. But because the forces involved are so enormous, even that tiny imbalance is enough to produce a force strong enough to move the hairs on your arm. In other words, what felt like a simple trick was actually a direct demonstration of the immense power hidden within electromagnetic interactions. Understanding this idea begins to change the way you think about everyday objects. Consider something simple like holding a mug in your hand. When you grip the mug, it feels solid. It feels like your hand is pressing directly against the surface of the ceramic. Your senses tell you that two solid objects are touching. But in reality, something very different is happening. The electrons in the atoms of your hand are pushing against the electrons in the atoms of the mug. These electrons repel each other extremely strongly, preventing the atoms from overlapping. This electromagnetic repulsion creates the sensation of solidity. Your hand never truly touches the mug in the way you might imagine. At the atomic level, there is always a tiny gap between the atoms of your skin and the atoms of the ceramic surface. The feeling of touch is actually the result of electromagnetic forces pushing back against your hand. This idea may seem strange at first, but it leads to a remarkable conclusion. Every physical force you feel in everyday life is ultimately electromagnetic. When you push against a wall, the resistance you feel is caused by electromagnetic repulsion between electrons. When you sit on a chair, the chair supports your weight because the atoms inside it resist compression through electromagnetic forces. Even the sensation of pressure when you press your fingers together comes from electrons pushing against electrons. In a very real sense, humans have never truly touched anything directly. Every interaction we experience is mediated by invisible electromagnetic forces acting across incredibly small distances. The same force that made your arm hairs move toward a piece of plastic is also responsible for the stability of matter, the sensation of touch, and the structure of the physical world. And once you begin to see the world this way, the ordinary objects around you start to look very different. Because beneath their solid surfaces lies a constant and powerful dance of attraction and repulsion between countless charged particles. That hidden interaction is what makes matter behave the way it does. And it is also the foundation of electricity. To understand how electricity actually works in everyday life, let's look at something very familiar: the wires inside your home. Imagine a copper wire running through the walls of your house. At one end of the wire is an electrical outlet, and at the other end there might be a lamp plugged into it. You flip the switch and instantly the lamp lights up. Most people picture this process in a very simple way. They imagine electricity flowing through the wire like water moving through a pipe. According to this common explanation, electrons enter the wire at one end, travel along its length, and eventually reach the lamp at the other end. It sounds reasonable, but that picture is actually misleading. Electrons inside a wire do move, but they move incredibly slowly. In a typical household electrical wire, the average speed of an electron drifting through the metal is only about 1 millimeter per second. At that speed, an individual electron would take a very long time to travel from one side of your house to the other. If electricity really worked like water flowing through a pipe, your lamp would take many minutes to turn on after you flip the switch. But that is not what happens. The light turns on almost instantly. So something else must be happening inside the wire. The key idea is that the wire is already full of electrons before you ever flip the switch. Copper atoms naturally contain electrons that are free to move around inside the metal. These free electrons form a kind of mobile cloud inside the wire. When the switch is open, those electrons are moving randomly, but there is no overall direction to their motion. The moment you close the switch, something changes. The power source connected to the wire creates a difference in electrical potential, which we call voltage. This voltage applies a force to the electrons inside the wire, pushing them in a particular direction. But electrons repel each other strongly. So when the electrons at one end of the wire are pushed forward, they immediately push against the electrons next to them. Those electrons push against the next group, and the effect continues down the entire length of the wire. It is similar to a long line of people standing shoulder to shoulder. If you push the first person in the line, the push quickly travels through the group. The person at the far end feels the movement almost immediately. The people themselves do not run across the line. Instead, the force travels through them. Electricity works in a similar way. When you close the switch, the electrical force propagates through the wire at nearly the speed of light. The electrons themselves drift slowly, but the signal that pushes them spreads extremely fast. That is why the lamp lights up instantly. The electrons already inside the lamp begin moving as soon as the electric field reaches them. But this raises another interesting question. Where does that push come from in the first place? If the electrons inside your house are being pushed, what is actually causing that force? To answer that question, we have to trace the electrical system back. Your lamp connects to an outlet, which links to the vast electrical grid. The grid eventually leads to a power plant. Inside, massive turbines weighing many tons are spinning at incredibly high speeds. These turbines might be driven by flowing water, steam, or wind. That spinning motion is the starting point of the electricity you use. But how does spinning metal miles away push electrons in your house? The answer is the deep connection between electricity and magnetism. Electricity and magnetism are two aspects of the same force. When magnetic fields change, they can push on electric charges and make them move. Inside a generator, coils of copper wire rotate through strong magnetic fields. This motion exerts a force on the electrons inside the copper. Eventually, the electrons begin to flow. That flow is electric current. In simple terms, a generator converts mechanical motion into electricity. The spinning turbine drives the motion, the magnetic field applies the force, and the electrons inside the copper wire respond by moving. Once that movement begins, the electrical push travels outward through the power grid, racing through wires at nearly the speed of light. It works in both directions. Motion can create electricity, and electricity can create motion. This is the foundation of our modern world. In a motor, electrical current flows through coils within magnetic fields, producing the forces that drive everything from fans to electric vehicles. Imagine a dam where falling water turns turbines to generate power that eventually spins a fan in your home, miles away. It's a remarkable chain of cause and effect, linking distant locations through the invisible forces of electromagnetism. For example, if another coil of wire is placed close to the first one, the changing magnetic field produced by the first coil can push electrons in the second coil. Even though the two coils are not physically connected by wires, electricity can still appear in the second coil. This phenomenon is called electromagnetic induction. It is the operating principle behind transformers, which play a crucial role in electrical power systems. Transformers allow electricity to be transferred between circuits and can change voltage levels so that power can travel efficiently over long distances. Across the power grid, transformers constantly adjust electrical energy, stepping voltages up or down as needed to minimize losses and deliver electricity safely to homes and industries. All of this works because electromagnetic fields can transmit forces and energy through space. Metal interacts with metal across empty space, guided by invisible electromagnetic fields that surround moving charges. The everyday mechanical forces you experience, pushing doors open, lifting objects, walking across the floor, do not come from direct contact between solid objects. They are consequences of electromagnetic interactions. When you push against a door, electrons in your hand repel electrons in the door's surface. That repulsion prevents the atoms from occupying the same space, creating the resistance you feel. When you stand on the ground, the atoms in your feet push against the atoms in the floor through electromagnetic forces. That interaction supports your weight and keeps you from falling through the surface. Even the simple act of seeing depends on electromagnetism. Light itself is an electromagnetic wave. When light enters your eyes, the oscillating electric and magnetic fields interact with electrons inside the cells of your retina. Those interactions trigger chemical reactions that send signals through your nervous system to your brain. Chemistry works because of electromagnetic attractions. Heat exists because atoms vibrate. Biology emerges from chemistry, which ultimately depends on electromagnetic interactions. Nearly every process you experience in daily life traces back to this single fundamental force. Understanding this leads to a powerful realization. The physical world does not behave the way our senses suggest. Objects seem solid and separate, but at a deeper level they are structures held together by fields and forces. Matter is not simply blocks of solid material pushing against each other. Instead, it is an intricate system of charged particles interacting through electromagnetic fields that fill all of space. Electricity is simply one of the most visible ways humans have learned to harness those interactions. By guiding the motion of electrons through carefully designed materials, we can transform energy into light, motion, heat, and information. And this ability to control electromagnetic forces has reshaped the entire course of human civilization. But the deeper implication is even more profound. To truly understand electricity, we must accept that the universe itself is built from fields and forces that act across space, connecting distant objects in ways that would once have seemed impossible. To truly understand electricity, we must accept that the universe itself is built from fields and forces that extend through all of space. Charged particles do not need to physically touch each other to interact. Instead, they influence one another through electromagnetic fields that fill the environment around them. Once you begin to see the world in terms of these fields, the ordinary actions we perform every day start to look very different. Think again about something as simple as flipping a light switch. From the outside, it appears to be a small mechanical action. Your finger presses a piece of plastic, a metal contact closes, and suddenly the room fills with light. But hidden behind that simple motion is an incredibly complex chain of electromagnetic events unfolding almost instantly. When you flip the switch, you close an electrical circuit. That circuit already contains countless electrons inside the copper wires. These electrons are not sitting still. They are constantly moving randomly within the metal. However, without a voltage difference, there is no overall direction to their motion. The moment the circuit closes, the power source connected to the wires begins exerting an electric force on those electrons. That power source may be connected to a generator located miles away at a power plant. Inside that generator, a turbine is spinning continuously. That turbine might be driven by steam produced from burning fuel, by water falling through a hydroelectric dam, by wind turning large blades, or even by nuclear reactions producing heat. Regardless of the source, the turbine's motion causes copper coils to rotate through strong magnetic fields. As those coils move through the magnetic field, the changing magnetic environment pushes on the electrons inside the copper wire. The electrons respond to this force and begin to move. That motion becomes an electric current flowing into the transmission lines connected to the generator. From that moment onward, the electrical push travels outward across the power grid. It spreads through transmission lines, stretching across landscapes, through substations and transformers that regulate the voltage, and eventually into the distribution lines that connect neighborhoods and homes. The electrons themselves move slowly, drifting through the metal at speeds that are almost unbelievably small. But the electric field that pushes them spreads extremely fast, moving through the system at nearly the speed of light. By the time you flip the switch, that electromagnetic signal has already propagated throughout the entire circuit. The electrons inside the wires of your house begin responding almost immediately. Inside your lamp, electrons are forced through a thin filament made of a material that resists the flow of electric current. This resistance is crucial. As electrons pass through, they collide with atoms, transferring energy and causing them to vibrate intensely. This energy raises the temperature of the filament dramatically until it becomes so hot that it begins to glow, emitting electromagnetic radiation. Some of that radiation falls within the visible portion of the electromagnetic spectrum. That visible radiation is what we perceive as light. When those light waves reach your eyes, they interact with cells in your retina, triggering signals that your brain interprets as the sensation of seeing. At every stage, from the spinning turbine in a power plant to the signal in your optic nerve, electromagnetic forces are responsible. For centuries, this force was a mystery, but once harnessed, it transformed human civilization, allowing cities to thrive long after sunset. Electricity is part of a larger framework of interactions that shape our world. It is the fundamental force that powers our modern life. Eventually, the same electromagnetic principles made modern computing possible. Billions of tiny electronic switches inside microprocessors manipulate electrical signals at incredible speeds, allowing computers to process information and perform complex tasks. Nearly every technology that defines modern life depends on our ability to generate, control, and direct electrical energy. And at the center of all of it lies the same invisible interaction between charged particles and electromagnetic fields. Electricity is simply one way humans have learned to organize and use that interaction. But to fully appreciate what electricity really is, we must go even deeper, because electricity is not a substance flowing through wires. It is evidence that the world itself operates through invisible forces connecting particles across space. When people imagine the physical world, they usually picture solid objects interacting through direct contact. A hand pushes a door, a foot presses against the ground, a tool strikes a surface. Everything appears mechanical, as if the universe were made of tiny solid pieces colliding with each other. But that picture is not truly accurate. At a deeper level, the world is not built from solid contact. It is built from fields and forces. Particles influence each other across space through these fields, creating the interactions we observe as physical events. Electricity is one of the clearest demonstrations of this hidden structure. When you see a small piece of plastic attract bits of paper after being rubbed, you're witnessing the electromagnetic force pulling charged particles across empty space. When you flip a switch and a light turns on instantly, you are watching electromagnetic signals travel through wires at nearly the speed of light. What looks like a simple action is actually a complex chain of interactions between charged particles and fields. And once you recognize this, your view of the physical world begins to change. Solid objects are not truly solid in the way they appear. They are arrangements of atoms held together by electromagnetic forces. Inside those atoms, charged particles attract and repel each other in precise balances that create stable structures. The sensation of touching something is not the result of atoms physically merging. Instead, it is the result of electrons pushing against one another through electromagnetic repulsion. Even the light that allows you to see the world is an electromagnetic phenomenon. Light is a wave made of oscillating electric and magnetic fields traveling through space. When those waves interact with electrons in your eyes, your brain interprets the signals as images and colors. In this way, nearly everything you experience is connected to electromagnetic interactions. Chemistry depends on electrons interacting with atomic nuclei. Heat arises from atoms vibrating due to electromagnetic forces. Biological processes inside your body rely on electrical signals moving through networks of neurons. Your entire sensory experience of reality is shaped by electromagnetic phenomena. And yet, the electromagnetic force itself cannot be explained in simpler terms. It is not made of something more basic. It is one of the fundamental forces of nature, alongside gravity and the forces governing atomic nuclei. Physicists describe how electromagnetic forces behave using mathematical laws. But at the deepest level, the force itself is simply part of the structure of reality. That idea may feel uncomfortable because it challenges the everyday intuition we develop from our senses. Our brains evolved to understand objects touching and pushing each other directly. The concept of forces acting across space is less intuitive, but the universe does not operate according to our intuition. Instead, it operates through fields that extend everywhere, allowing particles to influence each other even when separated by distance. When you flip a light switch, you are not just turning on a device. You are activating a chain of electromagnetic interactions that begins with spinning turbines, travels through vast networks of wires, and ultimately produces waves of light that reach your eyes. You are directing invisible forces that connect distant parts of the world. This understanding reveals something remarkable about human achievement. Only a few hundred years ago, electricity was a mysterious curiosity observed in small experiments. Scientists did not yet understand how electric charges behaved or how magnetic fields interacted with them. Through observation, theory, and engineering, humans gradually uncovered the laws governing these forces. We learned how to generate electricity, how to transmit it across enormous distances, and how to use it to power machines, communication systems, and computers. Modern civilization now depends on this knowledge. Every time a message travels across the internet, every time a city lights up at night, every time a motor spins or a device charges, electromagnetic forces are being carefully controlled and directed. What once seemed like mysterious sparks and static charges has become the foundation of global infrastructure. So the next time you flip a switch and a light appears instantly, remember what is truly happening. You are not just using a convenience. You are interacting with one of the fundamental forces of the universe. Electricity is not simply a resource or a technology. It is a window into the deeper structure of reality, revealing how invisible fields and charged particles shape the physical world. And the fact that humanity has learned to understand and harness this force is one of the greatest achievements in the history of science.